Good morning and afternoon, everyone. This is Farhan Hussain. I've been a product design engineer for many years, and this is week two of product design engineering fundamentals. We're going to learn about materials and their main properties. Sohan and Zaki are on the line, and we'll be having a discussion so that we have a deep look into different aspects of material selection in the design process. So it's very important to choose the right material for the right, application. You can't just randomly choose a material. You have to really think about why you're doing it. Sometimes it's a very simple reason because it's cosmetically good or because it's cheaper, and sometimes it's more nuanced. It has better corrosion resistance. It's a bit better at conducting heat for maybe thermal applications. So you really need to think about why you're choosing different materials. So one of the first elements we'll look at is density. Density describes the mass to volume ratio of that material. A more dense object is usually feels heavier for the same volume, and a less dense object feels lighter. Zaki, can you tell me and give me an idea of what you think? Give me an example of a less dense and a more dense material.
Let's say we take aluminum as less dense metal, and whereas if we take steel or um, cobalt, maybe it'll have more density compared to aluminum. So
Yeah, those are good examples. And I mean it's also relative because I can say magnesium is a less dense metal and aluminum is a more dense metal, right? So I think it depends on your frame of reference, but but this is a good thing to consider. What is your frame of reference as well, which is more along the lines of your application. Next is thermal conductivity. In this image, you can see that when you're taking a thermal image, there are different parts that glow a red, which is indicating more thermal activity. Sohan, what do you think it means to have good thermal conductivity?
I guess if a material has good thermal conductivity, it just reacts how well in situation where heat is involved. So I guess in your picture, it looks like a stove or some sort of machine where it's absorbing a lot of heat and I guess still functions well.
Right. And then give me an application you think good thermal conductivity would be important.
Um, well, I guess if you're thinking about metal bridges or where it's especially during summer days, it will absorb a lot of heat and still function well. Won't expand much and make the bridge collapse and stuff.
So I think you're perhaps mixing a few things there. I would say that a bridge, if you have less thermal conductivity, it's better because then you're not really changing much with the environment, right? So perhaps let's try a different one. Um, what else would you think would be a good, if a material has good thermal conductivity, it's a good thing.
Uh, Maybe a stove.
Okay. Why do you think that?
Um, or I guess for stove, you're using, well, depending on what kind of stove you're using, you need the place where you're putting your stuff to be heated to have good thermal conductivity because over time, when it's heating a lot, you don't want it to expand too much um, and
Yeah.
still function well.
I think you continually combine expansion with conductivity here, thermal conductivity. Let's not look at thermal expansion for now, or like that part of it, like the behavior of materials to change shape with the with thermal conductivity. But let's look at the stove idea. You use a pan, right?
Okay,
What material
right.
do we use make pans out of?
Uh, Metal
Yeah, why do you
mostly.
think it's metal?
Because it has, I guess, good thermal conductivity
Exactly, because
and
what you're trying to do.
durable.
Yeah, exactly. And you're trying to pull that heat from the stove into the pan and send that into the food, right? So that's an example of good thermal conductivity. Another one I would say is for heat sinks. If you're trying to cool different things, for example, the CPU of your computer, you'd want to have a good thermally conductive material to pull that heat away from that hot processor to the environment to cool it down. Next, we'll look at electrical conductivity, which is very similar. Zaki, tell me a bit about this. What do you think is a good electrical conductor, and where would you use it?
What about a capacitor? So it's a good electric conductor. It stores energy as well. So you can use it in phones, laptops, and such devices.
So a capacitor is a component. Let's talk about materials because capacitor would be made out of a material, but it's actually
Right.
not a very good example because it has some dielectric properties. We're not going to go into that right now,
Yeah.
but let's talk of another material that you think is a good conductor and why would you use it?
Right. It could be copper as well because it's a
Okay.
good conductor of electricity. You can use it for multiple stuff, like almost everything you can imagine.
Yeah.
Let's
So
say, you go on.
yeah, no, that's good. And it's basically the electrical conductor is you want to pull the electricity, and copper is a great example. And anywhere you want to pull electricity, you can use copper, copper could be a good solution there. All right. We'll stay with you, Zaki, because I know Sohan, you really like talking about thermal expansion, but we'll come back to you. But Zaki, what do you think thermal expansion is, and what
Right.
could
So
be the? Go on, sorry.
it's basically when they like a material or a metal, it reacts to temperature. So when it cools down, it becomes less in terms of it doesn't expand, right? It contracts basically.
Mm-hmm.
And then when it heats up, it expands, it loosens up. So
Yeah.
that's my understanding of thermal expansion.
Right. And there's good characteristics and bad characteristics of it. For example, a
Right.
good characteristic is you might want to attach a bushing or say a bearing or some sort of like tight fitting part over another. You can expand it with heat and have it slip onto the adjacent part and let it, while it cools, it contracts and it really tightens around that part. And a
Right.
bad example is perhaps the bridge that you're talking about, Sohan, where you need to design strategic gaps between parts, or else in that expansion, it'll collide and create catastrophic failure. So, Sohan, we'll talk about this strength. What do you think strength is? We spoke a bit about it before, and then give me an example of a material with good strength.
Strength is, I guess, a material's capacity to withstand load. So basically, how a material reacts to external load. And I guess a good one would be mostly like the good ones would be aluminum is a good one, or steel, or any heavy metal would have good strength. But, they would have different levels depending on their properties and stuff.
I would be careful with the term heavy metal because you don't want to invite any Metallica fans. No, I'm kidding.
That's
Metallica fans are welcome, but heavy metal can imply many other things. So what we were talking about more is metals generally have high strength. It's a good point, and steel is a really good example of high strength application. In this image, it appears to be a tensile rope cable kind of feature that is used to hold this column up, probably on a bridge. Okay, cool. Next is toughness. I'm going to stick to you, Sohan. What do you think toughness is, and why is that important?
I guess toughness is kind of relating to strength as well. It's more of how much um, load the material can absorb and still function well. And I guess is very important, especially with objects that are using or being used constantly. I guess for them to have toughness, good toughness for it to last and be durable.
Why do you think I use this image here?
I guess I'm assuming that's a phone or some sort of device, and the reason you used it is we often drop our devices. So if the material doesn't have enough toughness, it's gonna break if I drop it once, and you don't want that because I'm assuming a phone is a good long time investment that you want it to last for a bit.
Yep.
So
Cool. Perfect. Awesome. And hardness, I'll just talk about this one real quick. Hardness is just the ability to resist deformation. And here we have diamond, which is the hardest naturally occurring material substance. The bonds between the atoms are so strong that they just do not move apart, and it's a very good indicator of it's what's used. It's one of the ways to measure the hardness of a material. There are much softer materials, for example, calcium. Even the fingernail, for example, your fingernail can scratch, say, chalk, but there are other materials which it can't, or the opposite happens. If you scratch a nail, like a wall nail across your fingernail, it will scratch your nail, right? So there are various levels, but then if you take that nail, or if you take a knife and try and scratch the screen of your phone, you can't do that because the phone screen is harder. But then if you take a grain of sand and try and scratch the phone screen, the grain of sand will scratch this phone screen. And then if you take a diamond, you can scratch the grain of sand. So there's a scale, but there's also a reason, there's a benefit to have it more harder or less hard. We won't talk about that in this particular lecture, but something to consider. Ductility is kind of the ability for you to wire form and or stretch a material to become a certain shape. Here we have an example of wires, a steel cable, it seems. Malleability is, how easy is it to form into a shape. Here we have an example of heated metal, which aids in malleability. You don't need to have heat in some applications, but heat does definitely help. Corrosion resistance. I'm going to pause in this one. Zaki, tell me about corrosion resistance and tell me an example of a material you think has bad corrosion resistance.
Right. Corrosion resistance is basically when oxygen and basically moisture reacts to metal, and it corrodes on its surface, so it damages the surface, something like that. And I think steel is one of the worst metals amongst all of them, because I've often noticed in vehicles, when it's not coated properly, it just corrodes after a rainfall or something like that.
So I would say steel can be some of the best, actually, because you probably
Oh,
heard of the term stainless steel, right?
right.
So your knives and forks that you use are generally made out of stainless steel, but you can have a knife made out of carbon steel where it rusts very quickly, but it's much harder, and it's able to get a much sharper edge. So there's definitely a benefit there, but however, not to digress too much. An example for the car is most likely iron or something else similar to that. Or there are steels that are more or less corrosion resistant or pretty corrosive. So it could be that as well. But steel as a material classification is very broad. So I'd urge you guys to be careful when you classify any of your materials as steel. Really think about which steel grade you're using and why. Cool. So talking about material classifications and steels, let's talk about materials and their basic properties, specifically like specific materials and their basic properties. So we talked about steels, and steels have so many different properties. There's so many types of steels. There's 300 grade steels. There's stainless. In the stainless steel, there's austenitic. Austenitic. There's martensitic. There are different crystal structures inside of steels. There are different. Uh, the composition of steel, it can be so vast, right? And so steels are really versatile and durable, and they have so many great properties to them, but you really need to think about which one you're using for what application. We'll look in the next session, we'll look at examples of how we're going to be choosing a steel or in our specific application. But for now, just remember that there are so many types. There's so many that do various behaviors, and just be wary of which one you're choosing and thoughtful of why you're choosing them. Aluminum or aluminium, for our British friends. I actually have both spellings in this slide, but essentially it's a very lightweight, pretty corrosion resistant material that is used for avionics, for many applications. Is one of the best materials, very abundant in the earth as well, very easy to recycle. One of the best materials to use and there's also various grades of aluminum to choose from, different properties. For example, some are more formable into sheet metal parts, some are better for machining. So really good example. I don't have it here, but Sohan, can you give me another example of something that uses aluminum?
Bicycles.
Which part of the bicycle?
The frame that holds the tires. I guess especially higher end bicycles, the mountain bikers and the ones they use for racing and stuff, they use aluminum.
Yeah, so the frame generally, yes, that's correct. And then I'll give you another one, which is like a Coke can or a Pepsi can. They're made out of aluminum. But speaking of frames, the next, this I was going to go. There's another material coming up right after this one, but let's talk about plastics. Plastics is perhaps the most abundant material right now around us. Not on Earth. I need to double check that, but it's definitely in household products, in everyday products. It's perhaps the most abundant. You see it everywhere in various forms and applications and types. Literally, just look on your desk. You'll see different things. Like on my desk, I have like the keyboard itself is made out of plastic. My mouse cover, the speaker, probably the speaker, these knobs on my microphone, these knobs, many things around you. Zaki, can you give me an example of a plastic that is on your desk right now?
My own pen, which I write with, it's plastic.
Yeah, exactly. So plastics have so many different properties. It's very similar in the sense to steel in that case, where you can really have almost any properties. You can have them optically clear, you can have them biodegradable, uh, different colorings, different finishes. You can have like satin finishes and rougher finishes, or you can have glossy, matte. You can paint them. There's so many ways to use plastic. That's why they're very abundant, and so it's something to be thoughtful of. And when you're going to choose plastic for a material, you really need to dive into what plastic you're really specifying. And what's interesting is you can even fill them with other materials, like say with glass or with carbon chips, to make them have various additional properties. So plastics are complex but very cool and very useful in many applications. Composites. So yeah, speaking about bike frames, composites, very popular now. We use them for almost many applications because of their extreme lightweightness and quite frankly, almost alien properties in terms of stiffness and strength. In this case, this man is. It seems to be he. It seems to that he's cutting a sheet of carbon fiber, and carbon fiber is very popular in use for lightweight structures like planes and drones and such, and bike frames. And you'll see that there's a weave pattern. That weave pattern is used for aesthetics. That's true, but its primary purpose is actually to dictate which direction the tensile fibers are, to help you determine which way you're going to design your product to have stiffness or strength in that direction. So keep that in mind. Next is wood. I'm not going to talk too much about it, but wood is beautiful and it's used in basically all furniture, most furniture, and not so much in electronics per se, but in everyday life, very used. Actually, your home is probably made out of wood framing, so it's quite strong as well. So and naturally existing, so it's an excellent material. Glass. Glass is a type of ceramic which we'll talk about next, but it is transparent and usually very brittle, but it's very resistant to chemicals and weathering. Sohan, can you give me an example of a use of glass not shown here?
Laptop screens, phones, your watches sometimes have glasses.
Yeah.
A lot of the stuff.
And glasses, basically a drinking glass.
Yeah,
That's because you don't have any extra flavoring or material, or you don't taste glass, which is really good, right? So like when you drink out of say talking about soda again, if you drink it out of an aluminum can versus a glass bottle, generally you feel like there is a taste difference between the two. And that's because glass is quite inert and does not have any chemical reaction with fluids like other materials do. Ceramics, they're quite beautiful, very hard materials used in many applications. Sapphire crystal is one example where it is glass, it is a type of glass, and it is transparent. So ceramics is a broader version, or the broader classification, and under it is glass. But it's important to remember that it is a material classification on its own. It's very good for weather resistant applications. For example, hard screens where you have a lot of people touching it and rubbing their fingers and perhaps putting in their pocket, and there's keys there, and you don't want that to scratch that part. Glass is very good use there. You'll see most phones nowadays have glass in both the front and the back. And yes, while they are a little bit more brittle, they're much better at scratch resistance. And so that may be one of the reasons, on top of aesthetics, why these companies have chosen to do so. So I'm going to rush a bit more because I know that you have a hard deadline. Let's talk about rubber real quick, an elastic material that's used for many applications where you need impact or maybe more grip, and or even like sealing where you need some sort of deformation. Rubber is used everywhere for many applications around you. Concrete will be the last example here, used mainly for buildings, and it helps with creating a much better compressive member or compressive force in a compressive material in that application. So we're going to talk really quickly about important properties of materials for engineering. Number one, stiffness. We spoke about this a bit. It's the ability to not deform under a load. For example, if you have this roof in this design, if that beam was bending, then it will be kind of scary because you're like, oh no, the roof is coming down on me. So you need to choose a material that is very stiff and not just flimsy. Stiffness is measured generally with these two, and there's also one more which is called bulk modulus, but essentially Young's modulus, shear modulus, their equations, their formulas, and and these are good representations of the stiffness of the material, something that you really need to think about when choosing your material and your application. And when you have a table of choices, you'll most likely have stiffness as one of the reasons why you pick one material over another. But the other thing about stiffness is it can be affected by different things, and you can use a material and machining or material properties and manufacturability to their advantage. For example, you could perhaps shape some materials in certain ways where you can't do another, and you can maybe have some have thicker areas, thinner areas, and some have a different property based on the kind of manufacturing method you choose. So that can affect the stiffness, and you can improve it with those kind of addressing those kind of points. Next is strength. We spoke about this at the beginning, but it's also very important just to remind ourselves again that strength is the ability to withstand the load under the stress, and it's very similar to stiffness. So you can you can get confused with it, but it's the total ability, the ability to carry that load without breaking. And so it's very important to consider this property for your design. And a strong material generally is used for load bearing components. So just remember that if I have a load bearing design here, maybe I'm building a chair where there's one part that's going to be taking a lot of stress, I should make it a strong material, choose a strong material there. These are the type of ways we measure the strength of a part. We do tensional strength. You pull it apart and see where it fails and how it fails. You compress them together and you see if it buckles under that load, and you can shear them, which is kind of like tearing almost of the material apart. Finally, today we'll talk about toughness and its ability to absorb. We spoke a little bit about it earlier on. And toughness is really important because you want to have that material will have the ability to absorb impacts and shocks. For example, these players, they're wearing their helmets, they'll be colliding into each other, and you would want to protect their head and their body. And so you have a helmet which is pretty impact resistant and has tough materials inside of it and around it. There are various ways to measure toughness. These are just two of them, but it's impact strength and fatigue strength is just how long, how durable are these materials over time subjected to these types of loads. Awesome. So that was the lecture. I rushed through a lot of it because I wanted to make sure you can go to your next things. But before I close, I wanted to just open the floor to some questions. So, Han, you're muted if you're asking anything.
Sorry, thank you. Yeah, well, I guess I wanted to ask is when you're choosing a material for, say, you want to build a phone, and so how do you choose the material? Are you testing it out, or are you more of like just go with the information it comes with and kind of like how you taught us decision metrics and just kind of choose the material based off of that? Say you're trying to make something custom where you're going to be using different materials that hasn't been used in this product because it doesn't exist anymore.
Yeah, that's a very excellent question. I don't know if you know how insightful that question is, but it's a hard question to answer as well. There are some instances where you just ask the vendor, hey, here are some of the properties. You might go to a plastics vendor and ask them to give you or source the material for you based on some properties, right? And some of them are just gut feel, or some of them, or not gut feel, but like experience from using them before. For example, we know 316L is an amazing stainless steel for knife applications, for example, or for watches or something, right? But you might want to use something else. You might want to use a new material. That's where you open up experimentation, where you're like, okay, let me try and create a brand new alloy of steel, right? Then you can work with your engineers or research team and build experiments to see it's subjected through applications you see that material going through, or that part going through. Additionally, you can do due diligence, which is most recommended, where you try multiple materials and then see which one works best in your application, test it through those different like fatigue tests, for example, or reliability tests or corrosion tests, etc. All of the things that you care about. And then you can take it a step further and say, hey, these are 5 designs based on maybe 2 different materials, so 10 different options. Which one withstands these loads the best, or these circumstances the best? And that becomes very complicated, but that's the rigor you might need to do in some applications where you, for example, on a phone, millions of people are going to buy it. You're going to need to decide which material and which design and which manufacturing process, which coatings, which tolerances, all those things, which one of all of these aspects is the best one for me to ship to a customer to make sure that it's safe, good to use, and reliable, right? So I hope that answers the question.
Yeah, thank you. Appreciate it.